So we're going to have a presentation on Eyes in the Sky, the GPS system. You'll find out why I call it Eyes in the Sky later on in the presentation. But one thing about the GPS system, it's a cornucopia of technology. I see most of the people attending here today tend to be the people in the group that like technology. So this is going to be fun. Let's continue on.
All except one.
Who are we missing?
Gus doesn't like technology.
Oh, Gus, that's right. He doesn't have a computer. Okay. So the GPS system, we're going to talk about what it does, who operates it, who administers it, and who does it serve, and how does it work. Okay. We'll have how does it work towards the end because that's the most complicated part. But we'll continue on. So what does it do? So the GPS system is a system of orbiting satellites that give position, navigation, and timing data, both to the military and civilian users. The satellites orbit every 12 hours, and for an accurate location, you have to have your GPS receiver has to be able to receive 4 satellite signals in order to calculate time, location, and velocity. And they've developed receivers for almost everything: spacecraft, aircraft, ship, lands, vehicles, precision-guided munitions, hand carrying, except carrier pigeons. Apparently they don't need it. So let's see. So now the GPS accuracy. GPS-enabled smartphones are typically accurate to within about 16 feet. Okay. Now the GPS satellites are capable of sending 2 frequency signals. Actually, now the latest ones can send up to 5, but if you have a dual frequency receiver, you can get your location down to a few centimeters. Now an inch is 2.5 centimeters, so we're talking about down to about an inch. Okay. Right, and for long-term measurements, they say at the millimeter level. I'm not sure what they mean by long-term. It's probably on stationary objects, if your receiver is stationary as opposed to moving in a car. And the government commits to an error rate of about 6.6 feet. Now, this is smaller than what your smartphone can do, but that's because the smartphone doesn't have an accurate clock. The 2 things that are important with the GPS system is knowing the exact position of the satellite and having exact timing between the satellite and the GPS receiver. They really determine the accuracy. Now, this, I presume, is when you have there's a cesium clock in the GPS satellite that sends time signals, and I presume if you have a cesium clock receiver, which they have on the back of big trucks, you'll get 6.6 feet with the current GPS system. Okay. So now they're basically 24 satellites up about 11,000 miles high in altitude. They're launched from Cape Canaveral. It's now called the Space Force Station. You'll see Air Force and Space Force used interchangeably, depending upon what the website said. I left it up there because I have no idea when the name changed or what's going on. It's a little confusing right now. But it is the Cape Canaveral Space Force Station now. Same thing with Vandenberg, that's Vandenberg Space Station. Schriever Air Force Base is now Schriever Space Force Base. So there's a number of changes in facilities going on. So if the satellites transmit on 2 signals, remember, so we had a dual band receiver, they're up. L1 is at 1.57 gigahertz, L2 is at 1.22 gigahertz. Okay, and whoops. Ooh. Boy, good thing I'm not a brain surgeon. I'm gonna have to wheel that guy out. All right. So then, the constellation consists of 6 orbital planes with a minimum of 4 satellites per plane. So there are 6 different planes that the satellites orbit in, and there's a minimum of 4 in each plane, and that will give you the opportunity to see 4 satellites at one time anywhere on the globe. Now, as of June 26, 2022. There were 26 operational satellites in the GPS constellation, which means that 2 of the planes must have 5 of them in there. For some reason, they wanted more accuracy on that coverage. All right. So how did they get up there? Okay, well, the government used the Evolved Expendable Launch Vehicle System. Okay. And notice I have expendable in yellow, which means that when this rocket goes up, it delivers its payload, which is the satellite, and nothing else is usable on it. So it's expendable. There are two launch vehicles that are used in this system program, the Atlas V and the Delta IV. The Atlas V family is capable of carrying payloads of 19,620 pounds into geosynchronous orbit. Now, geosynchronous is 22,000 miles up. The satellites are only 11,000 miles up. And the satellites, the Block 3, which are the latest satellites, weigh 8,550 pounds. So you can see there's definitely a lot of margin there. I don't know what's used to support the satellite in the fairing, but it can't be that heavy, I don't think. So there's plenty of margin for getting that satellite into orbit. The Delta V family, again, is a heavier lifter, 23,851 pounds into geosynchronous orbit. And a lot of these, the Delta family, you can add little solid rocket boosters on the side to increase the payload. Okay. Now, Elon Musk and SpaceX and the Falcon 9 come into play. And this is the first time there's going to be use of a reusable rocket. Okay. In November 5th of 2020, GPS-3 Space Vehicle 4 was put up by SpaceX. And then in June 17th of 2021, 7 months later, SpaceX used the same rocket body to put up that satellite, and it was successful to put up Space Vehicle 5. So that means with the launch of Space Vehicle 5, it's the first time the Space Force officially enters the era of reusable rockets.
What is SpaceX again?
SpaceX is the
Name of the firm.
yeah, the company that Elon Musk owns.
Musk. Okay.
Yeah, that makes the Falcon 9 rocket. I think he put one of his cars into space around the sun or something. Yeah, they needed a payload, so I guess he wanted to get rid of the car. Maybe he got a tax write-off. I have no idea.
This rocket comes back and lands, right?
Yes, and I've seen videos where it lands on a platform out at sea, which is a neat trick. Okay, so let's take a look at some of the current and future generation satellites. The Block 2A, I don't know if you're familiar with the block system, they use it for airplanes also, but each block is an improvement over the previous one. The Block 2s have a general platform, and then there are some modifications, and then get to the Block 3, and that's an improvement over the Block 2s. And if you look at this chart, well, these are no longer in operation, but there's 7 Block 2Rs, and one of the things you can see is that 7.5-year lifespan design finally went up to 12 years in the Block 2F, and went to 15 years in the block in the GPS-3s and 3Fs. So they're getting more and more service out of the satellite itself. As you go from 2R to 2RM, they give you the second civil signal, that's L2, so that's where you can use the dual frequency receiver. Okay, and apparently there are new military M codes for enhanced jam resistance. I know Stu asked that question, I have no idea how that works, but that's the claim. And we see as we go to Block 2F that there's another third civil signal added to the satellite called L5, and this one is in the airline frequency range, the airplane frequency range, FAA. This one also has advanced atomic clocks, and 12-year design. When you get to the Block 3, 3F, they've added a fourth civil signal. Okay, I don't know exactly what that's used for. And 15-year design. And the interesting thing here is, all right, I'll cut my bet. We're gonna have.
That's not Air Force.
It sounds like Yonkers Raceway. But anyway, the 3F satellites have laser reflectors. And right now, they're currently using S-band radar to get the position of the satellites. When they get to the laser reflectors, the ground station sends up laser beam, and laser beam bounces off the reflector on the satellite, comes back down, it gives them a much more accurate position information on the satellite. And again, knowing the accuracy of the position of the satellite and the closeness of the timing between the clock on the satellite and the GPS receiver are the two most important factors for getting an accurate location. So now, how is all this controlled? Well, there's a GPS master control station, okay, and that's out in Schriever now Space Force based in Colorado. Okay, and there's a group called Delta 8. They're basically the ones for monitoring and controlling the GPS satellite constellation. There's also a global network of ground facilities that track the GPS satellites. These green ground antennas, and I think these yellow ones also. And there's a current operational control segment. This whole control segment consists of a master control station, 11 command and control antennas, and 16 monitoring sites. The monitoring sites make sure that the satellites are transmitting properly, and 11 command and control centers are used to transmit information to the satellite, upgrading software and things like that, and getting telemetry back on the condition of the satellite. So the master control station provides command and control of the GPS constellation. It's used to compute the precise location of the satellites. It also ensures the constellation health and accuracy. I guess you're constantly checking on the output of the transmitter and the solar panels, and how much fuel there is to jiggle the orbit of the satellite, things like that. They perform satellite maintenance. They can change the oil and balance the tires all in one motion. And anomaly resolution and repositioning of the satellites. That's important. They try to keep them evenly spaced to make sure that you can see them you can see 4 of them from any place on the globe. So basically, basically they're concerned with the accuracy and integrity performance standards of the satellite. That's the master control station out at Schriever. Okay, then you have all these ground antennas, all right, and they're there for sending commands, navigation data uploads, processor program loads to the satellites. They collect telemetry from the satellites, and different anomaly resolution. Now, Team Blackjack. Team Blackjack is the group that actually, out at Schriever, that actually operates the satellite. So the guys that pull the levers and push the dials. And they used to be Air Force 2nd Space Operations Squadron, and Air Force Reserve 19th Space Operations Squadron. I don't know if they've changed the names of this yet, but based on the data that I got, they're still called Air Force. Okay. Together, those two groups are nicknamed Team Blackjack. This is the team. This is Schriever Air Force Base. Here, they're watching as the last GPS 2F satellite was being launched. You can see it's a small control center. I guess all those people don't fit in this control center, so there must be office people as well, but it doesn't take that many to operate the constellation. But they basically control a worldwide network of monitor stations and ground antennas, and the monitor stations track the satellite's navigation signals, and they continuously monitor the precise location of the satellites themselves. Okay. Who administers it? Now, there's a big bureaucracy behind this. Well, it's not that big, but there has to be some bureaucracy behind this because it's a service. It's a service that's up 24/7, 365, and it's an evolving service. They keep adding more and more features to it. So the GPS program now is both a civil and military program. Before, it was originally just developed by the United States Air Force, but it's now has a large civil component, as you can tell. And it reports to the White House. It's under the White House, I guess because defense is under the White House, and the National Security Council, National Space Council, Office of Space Science and Technology Policy are all there. So the National Executive Committee for Space-Based Positioning, Navigation, and Timing is there as well. And there are a few offshoot boards that feed into it. Okay, so the deputy secretaries of all of these different departments in the government, defense, transportation, state, treasury, justice, interior, agriculture, commerce, energy, homeland, office of the director of national intelligence, joint chiefs of staff, and NASA all have an interest in the GPS system. They provide a member to the executive committee. Okay, and the executive committee meets at least once a year. There's an advisory board. NASA sponsors it. Okay, and it offers independent advice to the U.S. government on GPS-related policy, planning, and program management. And it also gives them information on national and international satellite navigation services. Now, there are other countries that have GPS satellites up. Russia has them. China is putting some in place. They've got a lot in place right now. And there are receivers that can use both GPS signals from the US and the Russian services, which means Russia has 24 satellites there also, so you can have up to 48 satellites and get an even more accurate position of where you are. But in this advisory board, we've got 28 members representing U.S. industry, academia, and international organizations. So you can see that the GPS system is not just U.S. focused and military focused, and it's not just U.S. Military and civil focused, it actually has international focus as well. There is input there. And that comes through so the National Coordinating Office, now this is the bureaucracy. They are a permanent staff in Washington, D.C. They support the day-to-day activities of the National Executive Committee, and they basically collect GPS-related information from these guys, okay, and then they also manage the interagency coordination, consensus development. I imagine all of these people have different requirements that they would like to see put into the system. So there's got to be some kind of consensus of what goes up when. And they're also involved with issue resolution. So this little piece here is the actual bureaucracy. This group here are basically members already of other departments. Now you've got the Civil Service Interface Committee, okay? And this basically represents the civilian part of the GPS system, private government, industry, both U.S. and international, okay? And they're there to exchange technical information, also do studies on civil uses and needs, and to identify any GPS issues that may need a resolution. So this is the civil part of the advisory system. Then you've got the International Working Group. This is used for developing, coordinating, and implementing international strategies related to GPS. Okay, they meet regularly. They have ongoing bilateral and multilateral cooperation activities. And there's international engagement. And the use of GPS, they're concerned about boundaries, the limitation of boundaries. That's important for a lot of countries. Fisheries enforcement. You know, when countries complain, your people are fishing in my backyard and my people are fishing in your backyard, you know, this helps keep them out of each other's backyard. It's an electronic fence that makes good electronic neighbors. Health information tracking. This was used during COVID. New York State actually had an app that could show you on GPS where the people were who had COVID and what stage of development they were in. Not too many people participated because they didn't want to advertise the fact that they had COVID, but it was there and there was an attempt to use it. It also involved remote sensing, geographic information systems, okay, and they involved in international consultations and negotiations with other nations. So that's basically the international focus of the GPS system. Then you get the engineering forum, and these are the guys with the squares. They're the technical ones. They make recommendations on technical issues. They have a framework for interagency communication. They address issues and opportunities that affect civil, joint, and international use. And they develop technical recommendations by consensus. So this is the techies. And then there's an ad hoc working group. There was no real explanation of what that was, but I presume it is what it's called. Groups that can be formed to deal with issues that the other groups can't. So here you have the executive committee. Here you have the office staff, basically. Here you have the techies who are evolving the system. Here you have international input from the rest of the world about what they would like to see. Here you have civil input from the United States and what they would like to see. Ad hoc group, NASA advising. It's good that they're tapping into their technology and expertise. And all these guys trying to get satisfactory use out of the system. So who does it serve? Well, it serves everyone because the signal is all over the earth, and if you have a GPS receiver, you can use it. It's not scrambled in any way, so it's usable. When it comes to private industry, it has a lot of cost benefits. Approximately $1.35 trillion were saved between 1984 and 2017 in 9 industrial sectors. These are those sectors, these are the savings. And you can see the biggest one is telecommunications, with improved reliability and bandwidth utilization for wireless networks. So I guess it was important in positioning the towers for the cell phone system. Okay. Military. What are the military uses? Well, there's a thing called JPADS, which is the Joint Precision Airdrop System. Here we have the staff sergeant watching as supplies are being dropped in Afghanistan. All right, and that's a great thing. These things have GPS location for where they drop, and then they can transmit their GPS location. It'll be easy to find in case you lose them in the mountains somewhere. GPS is also used in the guidance of unmanned systems like UAVs. It's going to be used in any vehicle that would be autonomous. If you can have an autonomous tank or an autonomous jeep or whatever, any robot. Navigation, of course, for the military, the aircraft, vessels, vehicles, personnel. Weapons targeting, smart bombs. With an accuracy of 1 inch, you could drop a smart bomb right down somebody's chimney if you wanted to. Oops. There we go. Let's back up. And forward. Okay, and command and control. You can find out where your personnel are located, which is a great convenience. You can watch them on a map as they're moving. So now the civil use of the system. All right, this is why I called it eyes in the sky, because you can track pets, elderly, children, criminals, vehicles, and property. So if you can slap a GPS receiver onto this, and one that can transmit its location, like your cell phone, you can follow these people around. So the satellite isn't actually watching you, but it's making it possible for you to be watched and tracked on the map. In navigation, of course, hiking. You know, if somebody carries a GPS receiver and one of those solar-powered battery chargers, there should be no reason why they get lost in the woods anymore. You know, search and rescue should be a thing of the past. Okay. Route planning. When I was coming down here, I planned a route that would take me 2 hours and 8 minutes, and I gave myself 15 minutes extra time. As I came down, I was headed on Route 17 onto the thruway. My GPS Google map popped up and said, there's an 8-minute longer route, but you don't have to pay the toll. So I said, I got the 8 minutes. So I took that route, and I avoided the toll, and actually it was a much nicer drive because it was in a more country setting instead of all the crazy people doing 80 and 85 on the thruway that try to get around you. Emergency road assistance like OnStar, and you hit that button and they know exactly where you're located. Locating businesses in your area. You can say, hey Google, where are all the Italian restaurants in Florham Park? And you'll start to get a list of restaurants in Florham Park, so that makes life very easy. Physical fitness apps, of course, both walking and running. I use one. You can tell how many calories you burn up. You put in your weight. You know how far you walk. You can figure out roughly how many calories you're burning. All right, now we're ready for the video.
The video?
Yep.
Okay.
Let's see what happens. This is a 6.5 minute video. It kind of does a recap.
Nearly every bit of data we use in our modern devices has a price tag associated with it. But there is one vital piece of technology that many of our devices depend on that is free. It allows our phones to give us turn-by-turn directions no matter where we are in the world, and it may one day even facilitate driverless cars. This, of course, is the Global Positioning System, or GPS for short. This satellite constellation cost upwards of $12 billion to build and launch, yet its service is available for free worldwide. Well, not really for free. The US taxpayers paid for it and continue to pay approximately $2 million a day to maintain and operate the system. But it wasn't always available for use. These satellites were launched for use by the military, to provide all divisions of the military with pinpoint accurate location information on their aircraft, ships, and even their individual soldiers anywhere on the planet. The first global positioning satellite, the Navstar 1, was launched on February 22, 1978, aboard an Atlas rocket. Over the next 7 years, another 10 GPS satellites were successfully launched into orbit. Only one of the 12 planned, Navstar 7, failed to launch. These Block 1 satellites validated the system's capabilities, and the lessons learned from the project were carried forward to the Block 2 satellites, which will complete the 24-satellite constellation, providing worldwide GPS coverage for the US military. A 24-satellite constellation ensures that at least 4 satellites have a direct line of sight with any point on the planet's surface at all times. This ensures the GPS constellation can pinpoint your location anywhere on Earth through trilateration. We know exactly where the satellites will be at any time as a result of predictable orbits and a ground station regularly checking in to make sure they are where we expect them to be. GPS satellites constantly broadcast a radio signal, which the GPS receiver in your phone is constantly listening for. This signal tells your phone the satellite's position and what time it was sent at, thus allowing the receiver to calculate how far away it is from the satellite, as the radio signal travels at a known speed, the speed of light. Each satellite tells us we are within X kilometers, and thus we know we are somewhere on the circumference of a sphere with a radius equal to that distance. Getting this information from 4 satellites allows us to pinpoint exactly where we are on Earth by combining each sphere and seeing where they intersect. Knowing the exact time is essential to making this system accurate. A divergence of 20 to 30 nanoseconds would make the distant measurements unacceptably inaccurate. So each satellite contains an atomic clock, the most accurate timekeeping device available. But due to their size and cost, these cannot be used in phones, so the GPS satellites also constantly update the phone's time to ensure it is able to calculate the distance between itself and the satellite accurately. To keep this time measurement accurate, we even have to consider the effects of special relativity, because the receiver on the ground is moving slower than the satellite in orbit, which is travelling at 14,000 kilometers per hour. Special relativity predicts that the onboard atomic clock will experience time slower, and thus fall behind the clocks on the ground by 7 microseconds a day. Furthermore, the satellites are orbiting at 20,000 kilometers above the surface of the planet, where the gravity of Earth has less effect on the curvature of space-time. And general relativity tells us that the clocks closer to the mass of Earth will fall behind the ones in orbit. So if we calculate the time dilation due to gravity on the Earth's surface, and then calculate the dilation at 20,000 kilometers from the planet's surface, we can see that the clocks will diverge by 45 microseconds every day. Combining these effects, we have to make the clocks on board each satellite to tick 38 microseconds faster than those on Earth. If this effect wasn't taken into account, GPS calculations would lose 10 kilometers of accuracy each day, making it completely useless. But thanks to the efforts of those ingenious engineers and Einstein's incredible discovery, we have a global positioning system on our smartphones with an accuracy within about 5 meters. But as I said earlier, this system wasn't always available to the average citizen. It was for military use only. To open this system up to the public would open a tool that could potentially be used against the US. After all, missiles use this system for navigation too. The incentive to open its use for civilian use came in 1983 when a Soviet Su-15 shot down a Korean passenger jet that strayed from its intended route into Soviet prohibited airspace, an error that could have been avoided had the new form of navigation been available. And so, on September 16, 1983, President Ronald Reagan announced the global positioning system would be made available for civilian use, free of charge. But there was a catch. The signal would be scrambled to decrease its accuracy to around 100 meters, making it useful but not by today's standards. This was intended to keep the US military's tactical advantage and prevent the system from being used for nefarious purposes. It wasn't until 2000 that President Bill Clinton signed a bill to stop this scrambling and open accurate GPS to all civilians, including those outside of America. This was done in recognition of the huge economic benefits GPS could provide to companies in America. American armies have disrupted the signal in the past in areas like Iraq by blasting out radio waves that disrupt the radio waves incoming from the satellites. And this isn't a difficult thing to do. In 2013, a truck driver in New Jersey wanted to mask his GPS location from his boss and used a small jammer, but inadvertently interrupted GPS navigation systems in Newark Airport every time he drove by. Beyond this simple jamming technique, which is easy to track, the US could simply choose to take away this privilege at any point and cripple businesses across the world. So countries around the world have been building their own GPS systems. Russia has its own 24 satellite constellation, and so does not depend on the US at all. A similar system will be available for China and Europe in 2020, while Japan has 2 satellites in orbit to increase GPS availability in its urban canyons. These satellites' orbits have been tailored to ensure that one is directly overhead at all times. Finally, India has 7 of its own satellites to cover India's land area alone. This tool is probably one of the most underrated results of the space program. A simple radio signal that allows our farmers to operate driverless tractors to manage their land. Commercial fishing vessels use it to navigate and find fishing locations. The aviation industry uses it for navigation and collision avoidance. Even drones would not be possible without it, as anyone who has flown a DJI drone knows that you have to have a connection to at least 6 satellites to fly. Another technology that...
The end.
What
Okay.
about the written quiz?
There's no quiz. Anybody have any questions?
That was really cool.
That was great.
Again, one thing about the GPS system is it covers a whole range of technology. You've got the rockets that put it up in space. You've got the S-band radar that's monitoring where the satellites are. You've got telemetry coming down from the satellites. You've got cesium clocks that are keeping time. You've got effects of special and general relativity. Okay, so all of this whole combination of disciplines has come together.
And drones.
And drones.
And geographic information systems.
Yeah, exactly. It feeds all of that stuff.
What limits now the 15-year lifetime? Is it the amount of fuel because you're always having because you're not a geostationary position?
Right. It drifts because the gravitational pull of the Earth varies over the Earth, and so satellites actually up and down, and they tend to go faster and slower. Right, and you want to keep the constellation, the distance between the satellites, reasonably constant, so that you can always see for them as they go over the horizon.
Hey, you.
So
and I'm assuming that it's
like fuel,
yeah,
simple thing.
because one of the slides I had up, the weight of the GPS 3 is like 8,500 pounds. Now that's the weight fully loaded, and then in orbit, the dry weight they call it is 5,002 pounds. It must be 3,500 pounds of fuel in the rocket.
Yeah, I think the issue of the Air Force magazine was talking about in the future they would use nuclear fuel, so the satellites would last longer.
Yeah, there you go. That's up. But right now there are treaties about putting supposedly nuclear substances up in space because
You don't know where it's gonna come down.
and the Russians dropped a few in Canada, fortunately, in isolated areas. But I guess if you make
That's
large enough shield, then we've got big rocket capacity to put them up there. So we'll see what happens. I know that I think that the old Viking satellites that they sent out past Mars and did a survey of the planets and are going out past the
You had
Voyager. That's it,
I
Voyager.
think it was the Cassini mission.
And it's
left
still
Earth,
sending.
went to
And it's-
Venus
yeah.
and came back and went around Earth. Everybody was demonstrating.
I think the Voyagers had nuclear
Voyagers,
powered
yeah.
satellites, so they knew they were nuclear powered because
Because
they knew
outside the Oort cloud.
Yeah, exactly. It's going to be beyond our solar system and out into open free space.
RTGs.
And of course, there's no sunlight there, so they had to have some source of power.
Right.
And they didn't want a chemical source because that would run out right away. So they used nuclear powered reactors. And that was in the 70s. I'm not sure if it violated any treaties, but maybe Art would know because he's a international
Violator.
criminal anyway. But
Okay. Thank you, Toby.
That was great.
yep.
All right.
That was great.
Yeah.
Thank you.
That coin, right?
So, here, Toby.
Toby, thank you, Toby.
Thank
You
you.
want me to take off my
Okay.
hat?
No, leave your hats on. That's it. Okay, everybody, big smile. Okay, great. Okay, thank you. You got it.
All right.
All
Never
right.
mind, we're holding on to it a little bit.
No, it sure is.
Thank you.
I don't know what the hell it is. It's Howard. Howard does all. Oh, okay.
75th anniversary.